All right, so today we're looking at force of energy, force of gravity, and energy. All right, so here I have this golf ball. Now, I look at this golf ball, and the golf ball is attracted to me. All right, I am attracted to the golf ball. I like its dimples. Now, the reason why me and the golf ball are attracted to each other is that me and the golf ball both have mass, and gravity is the attractive force between any two bodies that have mass. So I have mass, the golf ball has mass, therefore we both have gravity pulling each other pulling us towards each other. However, if I let go of the golf ball doesn't go towards me, it goes to the ground. Because even though I'm attracted to the golf ball and the golf ball is attracted to me, there's someone else out there that the golf ball is more attracted to, and that is the Earth. And the reason being is the larger mass there is, the more gravity there is. And the Earth is more massive than I am, therefore there's a stronger force of gravity between the golf ball and the Earth than there is between me and the golf ball. So even though there is a force of attraction here, there is a stronger, much stronger force of attraction there, and the golf ball goes to the Earth. All right, so one of the things that affects the force of gravity is how much mass there is. The more mass there is, the more gravity there is. So that's why, like, the Earth has more gravity than the Moon. Weight is determined by gravity. On the Earth, like if you weighed 120 pounds, on the Moon, which has about 1/6 the mass, you'd have about 1/6 the gravity, so you'd weigh about 20 pounds on the Moon. All right. So more mass equals more gravity. And over here is just basically a little formula that shows you the relationship, right? So the mass is on top, distance on the bottom, force of gravity over here. So if I increase these mass numbers, that would increase the force number over here. So more mass equals more gravity. I double the mass, I double the gravity. All right, the other thing that determines gravity is how far apart two objects are. So I'd mentioned before that on another day that the gravity from the Moon and the Sun is what causes the tides on Earth. Now, even though it's a combination of the two, the Moon actually has more of an effect on the tides than the Sun does. But the Sun's a lot more massive than the Moon is, but the Moon is a lot closer than the Sun is. So how far apart two objects are determines gravity as well. The farther apart they are, the less gravity there is. The closer they are, the more gravity there is. Now this is what's called an inverse square relationship. And what that means is, well, let's say here's the Earth right here. And there's the Sun. And there's the Earth. All right. Now, when we're measuring things, when we're measuring distances in our solar system, it's not practical to use kilometers because like millions and millions of kilometers. So the unit we use when we're measuring things in our solar system, we usually use a unit called an astronomical unit, or an AU. So 1 AU is equal to the average distance between the Earth and the Sun. So the distance between the Earth and the Sun is 1 AU. Now, let's say I somehow was able to magically move the Earth twice that distance from the Sun. So instead of 1 AU, it was, take that distance, I double it. So the Earth was 2 AUs away from the Sun. All right. Now it's farther apart from the Sun, so if it's farther apart, there's going to be less gravity. But you might think that if I double the distance, the gravity would be 1/2. But that's not the case, because if I look at my little formula here, it's not, the distance is the distance squared, all right? So if I double the distance, it doesn't become 1/2. The distance is 1/2 squared, which is 1/4 the amount of gravity. So these two here, if I double the distance, there's 1/4 the amount of gravity here between them than there is right there. All right. Now let's say I was able to magically able to take the Earth and triple the distance. All right. So now this is 3 times as far away from the sun as it is there. It's 3 AUs away. Now, again, a lot of times you might think that if I tripled the distance, it'd be 1/3 the gravity. But again, it's d squared, so it's not 1/3 the gravity, it's 1/3 squared, which is 1/9. So between here and here, the Earth would have 1/9 as much gravity between them as it is right there. And if I quadrupled the distance, it'd be 1/4 squared or 1/16 the distance. If the distance was 5 times farther apart, it'd be 1/5 squared, which would be 1/25 the distance, and so forth. So in other words, as 2 objects move farther apart, the amount of gravity between them drops tremendously. As 2 objects move close together, the amount of gravity between them increases tremendously. So the 2 things that affect gravity, how much mass there is, and how far apart the 2 objects are. Now, I have this ball here. All right. Using my golf ball again, because you can use a golf ball for a lot of things. If I'm holding my golf ball like this, right now it's not moving. All right. But it has a lot of potential to move if I drop it like that. All right. So right here it's not moving, but it has potential to move. All right. The energy of motion is kinetic energy. All right. The faster something's going, the more kinetic energy it has. So when I'm holding it right there, it's not moving, so it really doesn't have any kinetic energy. Potential energy is stored energy. All right, so I'm holding it right there. It's not moving. However, it has a lot of potential. If I take my hand away, it has a lot of potential energy in there, because when I take my hand away, that potential energy is going to let the ball start moving. So as I let go of it, what happens is the potential energy starts to turn into kinetic energy as it's falling down, because as it's falling, it's gaining speed and going faster and faster and faster. So it's gaining kinetic energy on the way down. However, it's running out of room to fall, so it's losing potential energy. Now that split second before the ball hits the ground, that's when the ball is going to be traveling the fastest, so it's going to have the most kinetic energy, but it doesn't have any room left to fall, so it doesn't really have any potential energy. All right. So on the way down, what's happening is it's gaining kinetic, but losing potential. That's what's happening on the way down. On the way up, it hits, and now it's bouncing back up. Initially off the bounce, it's going to travel very fast, but as it's going up, it's going to be slowing down. So as it's going up, it's slowing down, so it's losing kinetic, but it's getting higher and higher, so it's gaining potential. And then eventually it'll stop, so it has 0 kinetic and a lot of potential, then it starts to fall again. So what's going to happen as the ball keeps bouncing up and down is the amount of kinetic, the amount of potential, as this one goes down, that one goes up, and then as this one goes down, that one goes up. So as it keeps on bouncing, the amount of kinetic and the amount of potential kind of keep flip-flopping, what's there the most of. Now, when a planet goes around the sun, basically the same thing's happening. All right? Now remember, when a planet goes around the sun, where it's going to go the fastest is when it's closest to the sun, and it goes slower when it's farther away from the sun. So it goes slow, fast, slow, fast, slow, fast. It goes faster over here because there's more gravity between them because it's closer. It goes slower over here because there's less gravity between them, so it's farther apart. But anyways, when the planet's out here, that's kind of like me holding the golf ball up here, all right? It doesn't really have very much kinetic energy, but because it's farthest from the sun, it has the greatest amount of potential. Now, as the planet's moving towards the sun, all right, that's like me dropping the ball. Is the planet's going to start going faster and faster, so it's gaining kinetic, but since it's getting closer to the sun, it's losing potential. Until it reaches the spot where it's closest to the sun, that's where it's going to be going the fastest right there. So that is where it has the highest kinetic energy. However, it's reached the spot where it's close to the sun, so it's not going to get any closer. So that's where it has the least amount of potential energy. Right? So right there, it has the highest kinetic and the least potential. So with my ball analogy, that would be like that split second before it hits the ground where the ball's going really fast, but doesn't have a lot of space left to go. All right, now, the ball bouncing back up is like this right here. It starts off really fast, but then as the ball is bouncing up, it's going slower. Well, same thing here. As the planet's moving farther away from the sun, it's slowing down, so it's losing kinetic energy, but as it's getting farther away from the sun, it's gaining potential. So that's like the ball bouncing back up until it reaches that spot again, which is like the ball being up there, where again, it has the least kinetic, but it has a lot of potential. So when a planet goes around an orbit like that, it's pretty much the same as this ball bouncing up and down like that. The amount of kinetic and potential just kind of fluctuate back and forth. All right, so that is gravity and energy.